Video is all about solving equations or inequalities with the modulus function. So, starting with an example of solving the equation, the modulus of 2x minus 3 minus 1 is equal to x plus 1. So in blue on the graph there, we've got the modulus of 2x minus 3 minus 1. We know from the last video that the vertex is going to be when this is 0. So 3 over 2. The y-coordinate of the vertex is minus 1. And then the other more crucial thing that we're going to need to know for this video is that this part of the graph here has a positive gradient. So that's where this is positive. So we'll have a 2x minus 3 minus 1 for that part of the graph. And then for this part of the graph, that's got a negative gradient. So that's where this has been flipped. So that's where we've got minus 2x and a plus 3 with the minus 1 on the end there. And that's going to be really important because that's now going to allow me to find the points where it equals x plus 1. So, on the right-hand side, let's solve the equation when 2x minus 3 minus 1 equals x plus 1. So just simplifying that. Take the x away from both sides. Add the 4 to both sides. So that's one solution. That's the solution here when x is 4. For the other solution, for when the green part of the graph is equal to x plus 1. Again, let's simplify that green equation, minus 2x plus 2. Add the 2x to both sides. Subtract the 1 from both sides. And divide both sides by 3. So this here is the solution of 1/3. So those are the two solutions to this equation. Second example, we want to solve the equation the modulus of 2x minus 3 is equal to 3x plus 7. I've already drawn out the graph of the modulus of 2x minus 3. The vertex here is the coordinate 3 over 2. This part of the graph here is the part that's got a positive gradient, so that's 2x minus 3. This part of the graph here is the part of the graph with a negative gradient. So that's going to be minus 2x plus 3. And we want to solve when that is equal to 3x plus 7. So that's got a y-intercept of 7, which is going to be up here roughly. I know the y-intercept here is 3 because of this, so I know it's above that. Crucially though, the gradient of the line I'm going to draw needs to be 3. So it's going to be steeper than the green line that's got a gradient of 2. So while I'm drawing my line, I need to make sure that it's steeper. If I draw this line like this, that's wrong. It has to be steeper than the green line. So I'm going to draw it like this. This is steeper than that. That's a gradient of 2. That's a gradient of 3. Now, the crucial thing there then is that means that actually there's only going to be one solution to this equation because the red line is not going to intersect with the green line. So that's why one of the crucial things for solving these equations is having a sketch of the situation so that we can see very clearly how many equations there should be and also which equations we should use to solve it. So the sketch here not only tells me that the red line will not intersect the green line, so I'm not going to solve over there at all, but it's also telling me to use the minus 2x plus 3 being equal to the 3x plus 7. So I can then add the 2x to both sides, subtract 7 from both sides, and divide both sides by 5. So that is the one solution to this equation. This is the point here where x is minus 4 over 5. So just to repeat, having a sketch is really important for here. Really important you compare the gradients of what you're drawing so you can see how many solutions there should be and where they are. Next, we want to solve the inequality. The modulus of 5x minus 1 needs to be greater than 3x. Now, just to repeat, the diagram is really important here. So I'm going to draw this out. So first I'm going to draw the modulus of 5x minus 1. So I'm going to start off just by drawing 5x minus 1. So y-intercept of minus 1 is roughly here. A gradient of 5, that's pretty steep like that. This point here is going to be when y is 0. So x is 1/5. I'm now going to take the modulus of the graph. So this part of the graph is completely unaffected. This part of the graph is going to be multiplied by minus 1. So it's going to move to be like this, where it's intersecting at positive 1. So the yellow part of this graph has got equation 5x minus 1. The green part of the graph had its the magnitude changed. It got multiplied by minus 1 to give it a negative 5x gradient, which made it a negative 5x plus 1. Right, let me draw the 3x onto this graph as well. So notice there's no y-intercept there. It's going through the origin. And it's got a gradient of 3, which is less than 5. So that means it will intersect in 2 different places. It will be less steep than the yellow line. Right. So now I've sketched my graph. I can now see that the modulus part of the graph, this is greater than the 3x over here and over here. These are the bits of the graph where the modulus is above the red line. In this part of the graph here, the modulus is below the red line. So I don't want that. I want the bit of the graph where the modulus is above the red line. So I'm going to work out what this x coordinate here is, which is where the yellow part of the graph, 5x minus 1, is equal to the 3x, which is where 2x minus 1 equals 0. So 2x is 1. So this is the value where x is 1/2 at this point. So I can now say that if x is greater than 1/2, so if x has any of the values, so here's 1/2, if x has any of the values over here that are greater than 1/2, then the modulus will be greater than the 3x. Similar logic to work out this point over here. That's where the green line equals the 3x. Add the 5x to both sides and divide both sides by 8. And we find that at that point there, x is 1/8. So I can now say that if x is any of the values that are less than 1/8, then the modulus is above the red line. And there we go. I have solved the inequality by drawing a sketch and using the two different equations of the modulus graph, the yellow equation and the green equation. I've been able to find the values of x where they are equal to one another, and then I've been able to use my sketch to say that x needs to be either greater than 1/2 or less than 1/8 for the modulus to be above the red line. Next, we've got the red graph, which is the modulus of x minus 2a, and we're told that's equal to the blue graph, which is 6 minus the modulus of 2x minus a. And we need to find x in terms of a. So first, let's find the x coordinate here. So the red graph there has got a positive gradient. So I need it to be a positive x, and the minus 2a will stay as it is. The blue part of the graph should have a negative gradient, so I need it to be a minus 2x. I can see the gradient of the blue graph is negative at this point, so minus 2x. So I've got the 6 at the front. I'm changing that 2x to be a minus 2x, which means I'm changing that minus a to be a positive a. So just to repeat my logic there, because I can see that the gradient of the graph here is negative, I need this to be negative, so I need to change this to be positive. Right, solving this equation, then I'm going to add 2x to both sides. I'll then add 2a to both sides. And then I'll divide both sides by 3. So that is the value of x here in terms of a. What about this point over here? Well, that's where the blue line needs to have a positive gradient and the red line needs to have a negative gradient. Looking at the red line here, it's going down, it's got a negative gradient, so I need that to be a minus x, which means I need this to be a positive 2a. For the blue line, like I say, that's got a positive gradient at that point there, so I need to have a positive 2x. So I need to have the 6 at the front, I need a positive 2x. I haven't changed the 2x here, so I'm not going to change the minus a there. Add the x to both sides. Add the a to both sides. Subtract the 6 from both sides, and then finally divide both sides by 3. So that's the solution for x at that point there in terms of a. Final example for this video. And this is a slightly different example and a really common exam type question. We are told that the equation of the modulus of 2x plus 3 is equal to a half x plus k, and we're told that it has no real roots. So that means that this equation has no solutions. And we need to use that fact to find the range of possible values for k. So as always with these questions, we want to draw a little sketch so we can picture what's going on. So I'm first going to draw the 2x plus 3. So it's got a y-intercept of 3. It's got a gradient of 2. So it's going to look something like this. I can work out this point here because that's going to be when y is 0. So that's the point minus 3 over 2. I'm now going to apply the modulus to that. This part of the graph completely unaffected because it's already positive. This part of the graph here will get multiplied by minus 1, and so we'll move up there. Right. So that's the modulus part of the graph. What about the half x plus k? Now, I don't know what my y-intercept is here. I don't know what k is. It might be, for example, that k is here. A gradient of 1/2 means that the graph it's quite shallow. It's not very steep. It's certainly not as steep as my yellow line there. The yellow line has got a gradient of 2. So the red line I'm going to draw here of gradient of 1/2 is not very steep. So it might look something like that. This is the y equals 1/2 x plus k. And right now, the way I've drawn that could be suitable because the red line is not intersecting with the modulus graph. There are no real roots the way I've drawn that at the moment. So clearly for negative values of k, if k is negative, if my line was having a negative y-intercept, there are no roots to this equation. It's only when I get into the positive values up here where we start getting two solutions, where we start getting roots to the equation. So where does the situation change? No roots, no roots, no roots, no roots. When I get to the vertex, I've suddenly got one root now where it goes through the vertex. And then when I go above the vertex, I get more than one root. I get 2 roots. So the vertex is key with these questions. Let's use the vertex, which remember has got the coordinate minus 3 over 2, 0 in this situation. And let's work out the value of k when the line goes through the vertex. So the y-coordinate is 0. The x-coordinate is minus 3 over 2. 1/2 times minus 3 over 2 is minus 3 over 4. Add the 3 over 4 to both sides. So k is 3 over 4 when the line goes through the vertex, which is when there's one solution, or one root. So if k is equal to 3 over 4, there's one root to this equation. If k was bigger than 3 over 4, there'd be 2 roots to the equation. One here, one here. We want there to be no real roots, so we need k to be less than 3 over 4 down here. And so those are the range of possible values for k. K can be anything less than 3/4, and then there'll be no real roots. So with these type of questions, if we're told how many roots there are, and we need to use that to work out a value of a constant, draw a sketch, look at the vertex, and think about what the graph would look like, what the values of the constants would be if the line goes through the vertex, and then you can say what you need to say about the constants based on your sketch and the vertex.